you fix an epsilon greater than 0. And then if for all partitions P that are finer than a particular partition piece of epsilon, it is true that the sum, n equals 1 to infinity f of psi sub n delta x sub n, that's a Riemann sum, minus some number L is less than epsilon. So now I'm not saying that the norm of the partition is going to 0. I'm saying if there's some partition that's kind of a high water mark or a continental divide for all partitions finer. A finer partition means one that has more points, at least as many. Every point in piece of epsilon would have to be in every one of these partitions, and these can have more. So no matter how much I chop it up beyond this one, if this difference always stays less than epsilon, then it turns out that the Riemann integral is well defined as equal to L. This definition is stronger than the one based on the norm of the partition. The norm of the partition just says the little intervals are getting smaller and smaller. This one says you go find a partition, and then for every one finer, having more points, at least all of its points plus more, if it is true that this absolute value inequality remains valid, then the Riemann integral is L. And then you would write f of x dx equals L. So that's the apostle definition of the Riemann integral. And it is technically stronger than the norm-based one. And let's talk about that next week. It's very interesting. You guys have all had the, you know what Riemann's condition is? Dead. Still there. An even weaker way of building up the Riemann theory, and I'll let you do it, is have you explored upper or lower Darboux sums? You know what they are. I can see we have a lot of things to look at next week. Here's a function tooling along, and you'd like to find the integral from A to B. So you institute a partition, as we do. There's no magic in the partition subintervals being all the same. In fact, the great idea of the Henstock-Kurzweil integral is to have them specifically designed for the function that you'd like to integrate. And if you pick them right, it's even stronger than the big. And you can integrate the Dirichlet, or sorry, the Dirichlet. You know, 0 on the irrationals, 1 on the rationals. It's like, that's the famous function that can't be integrated with the Riemann integral. Can be integrated with the Vega integral. And since the Henstock-Kurzweil integral is stronger than that, it can be integrated with that by a clever choice of partition. What were we doing? The Darboux.
The dead guy.
Yeah, the dead guy. So they're all dead. Even poor Frankfurt is dead. He just died. Author of the text. He was in Chico State. And he's a measure, or was a measure integral guy. Which is an interesting part of analysis. So what you do is on this first partition element, you find the soup of the function, and then you find the soup here, and the soup here, and the soup here, and the soup here. Soup, 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 soup. Okay?
And flashback to analysis.
All right. take, in the ith subinterval here, if m sub I is the soup for x in, what should we call it? Delta xi is the ith interval, soup of f of x, right? Then mi delta xi sum I equals 1 to n is an upper Darboux sum corresponding to that partition. Okay? And then you do the same thing with the ints. Yeah. And then you make the following argument. If the limit as the norm of the partition goes to 0 of the upper Darboux sum equals the same thing for the lower Darboux sum, their common value is the Darboux version. Darboux, by the way, is like that. Their common value is the Riemann. So we have 3 shots at it. This is a particularly weak formulation. The Oslo formulation is the strongest. And then the one with the norm is weaker, and this is weaker yet. So let's talk about stuff like that next week. Would you please read the rest of chapter 1? When you get to the Norbert Wiener's presentation, it's pretty dense, so just do that for culture and the Feynman thing. But
Just one question.
do Cauchy, Riemann, Stieltjes, Lebesgue, and Hinsdorf Kurzweil. Look at Norbert Wiener and Richard Feynman and smile. Okay. Yeah, those are very specialized. Well, obviously, Big Feynman was doing path integrals in multidimensional spaces that had to do with quantum mechanics. And Norbert Wiener was an American physicist / mathematician who was trying to study Brownian motion. You know what that is? You have like, I don't know. You don't want to have a solution if you have an emulsion, like you're making or small one-cell animals, maybe your plants in water. They're small enough that there are the average force exerted by particles hitting them, water particles, whatever it gets. It's not so uniform. They're so small that they're jostled. You know, us walking around here, there's lots of air molecules in me, but I'm so big, unfortunately, that they don't push me one way or the other. Too massive. But if you're a paramecium swimming through water, maybe all the water molecules on your left suddenly decide they're coming your way because they're all oscillating thermally, right? And they might give you a bump that way, a bump the other way. And if you track these things under a microscope, it's this jostling and sort of random path that things take. It's called Brownian motion. And all the great physicists have studied that. Einstein and Wiener was interested in it as well. So he was trying to come up with some theoretical explanation of how it works. So there you go. Is this course what you expected? I couldn't have been more